Okay. First thing you need to know is what is conditional probability? Okay, and it's very specific. It has this very specific word in it. Does anybody know what conditional probability is already? Have you heard of it? It's conditional. Nice, nice. Okay, so the probability that an event happens, okay, that's not really surprising because that's what probability is. The probability that an event happens, comma, given, and this is the word I was talking about, another event already happened. Conditional probability, the probability that an event happens given another event already happened. And we have a symbol for this, and I think this is the last symbol of the chapter. It's a vertical line like this. So when you see this vertical line, you say the word given. So if I were to see this written down, this set of symbols, it represents the words, the probability of A given B. Okay, and there's a formula for it. The probability that A and B occur at the same time. So remember the little line across the symbol means it's A for and, over the probability that the second thing already happened. This just means you're narrowing it down to the possibilities only if B already happened. So you're dividing by the probability of B. And we are going to represent that on the table very specifically with a colored pencil. Again, this is the same table from Friday. You have self-reported male and female categories. Yes or no on the pierced ear. Does that make sense? Okay. Use both the table and the formula to find the probability of A given B. So I'm going to reread this. Find the probability that someone is male given they have a pierced ear. Interpret this value in context. And that's just going to be a little second grade conclusion sentence. Okay, so over here, we're going to do this twice. We're going to do from the table and we're going to use the formula. Probability of A given B. Okay, and if you're going to do this from the table, what you have to do is narrow your eyes to only the B option. So put a little arrow to B and shade the B section. Okay, in this problem, B is pierced ear. So shade the row where they have a pierced ear. Okay, and then what you have to do is ignore the rest of the table. So in my math 1 class, when we do this, and we do this in math 1, you probably don't remember, I literally take a Post-it note and cover up the rest of the table. You're only looking at the shaded portion. Okay, so what's the probability that someone is male looking only at these 3 boxes? 19 over 103, which is 0.18. Okay, so if you want me to break this down into teenager for you, you basically look at the second thing that's listed and you shade that part and then only look at those boxes. Okay, now we're going to do the same thing again. but using the formula that I gave you at the beginning. So probability of A and B over probability of B. Okay. So this means and this symbol. What number is in the box for someone who is male and has a pierced ear? What number is in that box? 19. Okay, so the probability of A and B is 19 over 178. Okay, and then the denominator is just pierced ear. What's total pierced ear? 103. And then you can do keep, change, flip, like I drilled into your head for math 3, or you can just recognize that the denominators are equal, so they cancel. And then you get the same numbers that you had from your shading. Okay. The probability that a student is male, given that they have a pierced ear, is 0.18. So all I did was just take the symbols, rewrite them into the words for the context of the problem. Do you have any questions about what we did so far? Anything at all? Does it make sense? Okay. Now what I need you to do is nothing. Hold on. I need you to just keep writing. I'm just gonna go right here for the moment because I see people still writing. What's wrong? What did I say? What did I write? Wait, what? Oh, no, it's not on. Yeah. No, it would be blue. It like glows blue. Oh, it's probably my fridge. Like a what? Oh. Oh, okay. Jackson starving. Okay, let's do this one, guys, and then I'll scooch it down so you can see this full part. Okay, we're gonna go slow. given that a person is female, find the probability that they do not have a pierced ear. Use notation, the table, and the formula. We don't need to write a sentence, but we're going to do the table and the formula. And this is where we're going to use our other color. So probability. Okay, this is the hardest part right here. Which thing comes first? So if this reads A given B, what goes in the front? Pierced ear. Okay, now pierced ear is B, but it says not pierced ear, so you write B complement. Okay, but you don't say B complement, you just say not B. Like if you're actually going to read this out loud, you just say probability of not B, so not having a pierced ear. Do you see what I mean? The little c means not. Okay, given. And this is the really part where my people who hate patriarchal stuff is going to get really upset right here because in this particular example, being female is just not male. That is really unfortunate. Should write this problem the other way around so that the probability of A is female. Okay, so this reads, what's the probability of not having a pierced ear given not male? Are you with me? Okay. All right, now what I want you to do is put this little arrow again, and then I want you to take your other color that you picked and make a little color key. You're gonna say that your shading in this for this part is gonna be this other color. So you're going to remind yourself when you come back to your notes later that, oh, this is this part shaded. And then I want you to tell me where should I shade? So I'm shading not male. So that's here. Ignore your blue shading. That's a completely separate problem. Then this is not an overlapping situation. That's why we're using two colors. Okay. And after you shade, it becomes really easy. So what's the probability? So what's the box for not pierced ear? 4 over 88 total. So basically saying just narrow your eyes to the shaded part only, which is 0.05. Okay, now we're going to use the formula. So both of the things together over the second one. I like to think of it that way when I try to do, if I try to remember the formula in my mind without looking at the formula sheet, I say probability of both over the second one. Because the second one is what you're narrowing it down to. Anyway, okay, so what is the not pierced ear, not male box? What number is in the not pierced ear, not male box? 4 over 178. And then what number is total not male? 88. And then keep change flip. Okay, so this bit is going to be our chapter one review, so go ahead and set this up. And we're gonna do our chapter one thing, and then I'm gonna narrow it down for you because we're just too lazy to make tables. Okay, let's go. Okay, here's the big question. Which one of the events is the explanatory variable? Okay, so look back at the original table. Gender or pure steers? Gender, yeah, okay, so think of it like, try to think of it as chronologically comes first, but then again, you really can't say that, especially in terms of my child. My child is listening to this, hi. Just saying. So, really quick funny story. My stepson's wife is pregnant, and we did this whole gender reveal party thing. And they went around to everybody at the party and they were like, what do you think the gender's going to be? And my response was, I think it's going to be something. And then they're going to change their mind 16 years later. No, that's my kid. That's what happened with my own actual child. It's funny because my child had that situation. So I was like, my only piece of advice, make sure to take a lot of baby pictures in neutral clothing. Neutral clothing. Because I had to spend a whole summer going back through baby pictures finding neutral ones. They're adorable. I actually did take a lot of neutral ones. Good parenting. Okay, anyway. All right. Create a conditional relative frequency table for the two-way table above. So we determined that gender is explanatory, which means we divide down. Shh. Okay, so in this box, what I'm saying is this box would be 19 over 90. Can you guys look back up at the table and see where the 19 over 90 came from? Perfect. Okay. And then this box would be 71 over 90. Do you remember doing this from chapter one? I remember a lot of you guys saying, how do I tell if I divide down or across? I remember that. Do you guys trust my calculator work from before you came to put these decimals? No. I'm just kidding. We do not trust you to type things in the calculator. Okay. Shh. All right. Now, if you remember from chapter 1, there's two things that you need to know first. Whatever direction you divide in, the totals should be 1. So I really didn't need to do this one. I could have just subtracted from 1, I'm saying. Okay. And then to determine independence, you look the opposite way. So if I divide down, I compare across. And I really just need to compare these, but you can compare all of them. And what you're trying to do is look to see if these are exactly the same. If these are exactly the same, then they are independent. These are wildly different, so they are not independent. Exact. Oh, you know what, Jackson? You're so smart. Do you know how smart you are? Before you came, I Googled exactly your question. I said, how close do the probability of A and the probability of A given B need to be independent? And it says there is no how close, they must be identical. If they're really close to each other, they could be weakly associated. So it's kind of like a weak, moderate, strong thing, but we're not going to say that. Okay, anyway, I knew you were going to ask. I can't write. It's fine. It's Monday. It's because I haven't done any writing in 3 days. So I said, no, the events, gender, and pierced ear are not independent. You are more likely to have a pierced ear if you are female, 0.955 versus 0.211. Okay, now what I'm going to do on the next page after you flip this is I'm going to appeal to you that I don't need to make this whole table to determine independence. Do you notice that I only really looked at two numbers? So why fill out the whole table, I'm saying? There's an actual formula you can use that you don't even need to make the table. So if I could find the probability of this and find the probability of this and just compare them to each other, I don't need to make a table. I don't need to do all that. I just need to look at two numbers only. Okay, which is great. However, the way that this is presented by College Board is really annoying. So I'm gonna have you highlight part of it to narrow it down for you. So if you could grab, if you have a highlighter or just use the colored pencil that you had out, it's fine. What's wrong? It's not a little bit of. You guys, I'm gonna come around and put table numbers up because I'm going to play Mrs. Talbot's game of chant for speeding for my second period. It's not for you. Remember when they broke that one again? Oh. It's called the Lewis. Broke it last. You did. And then Dylan kept it. That's her thing. They kept, him and Dylan kept playing with it and they broke it. Like every time, every time I get it. I have like 3 sets and they're all missing like one number.
Are you gonna wait table? I'm gonna get on.
Pizza?
Yeah.
Yeah, am I gonna bring the fries? No. Bring your fries? You want me to take I play game with kids, they put them to take a car with you. Yeah. All right. So I only see him like 5 minutes. All right. So I know. Oh, wait, hold on. No, I did. Okay. So we need to define independence. Shh. Independent events are events that do not change the probability of another event occurring. There's two R's in occurring, and I did not make room for the second R. This is terrible. There's 2 R's in occurring. Okay. So events could be independent, like because they have nothing to do with each other, like tossing a coin and rolling a dice. Like those would be independent, just common sense wise. Yes, honey. I don't know what's wrong with me. It's Monday. It's just Monday. Okay. Um, Thank you. I'm so sorry. Um, or it could be like, do you guys remember when we were doing the hat method and I told you to not put the slip back? Okay, if you put the slip back and mixed it up, that would be independent events because the denominator would not change that. So if there are 10 slips of paper, I took one out, then there was 1 out of 10 chance of being chosen. But if I put the slip back and mixed it and then took it out, it'd be 1 out of 10 again. Do you know what I'm saying? So it means that your options did not get reduced. Now, for me, I don't know about you, but I look at this and my eyes glaze over and I can't do it. I can't do it. Okay. What this is saying right here, I want to show you guys my last year's notebook so I don't have to flip back and forth. But what this is saying right here is like this box in the table. And what this is saying right here is this box in the table. So it's saying if this equals this, then they're independent. Okay. However, we don't really need to even go that far. What I want you to do is take your highlighter and just narrow it down to this. I find that there's never a time, given the AP tests I've seen, given the homework I've seen in the books, given all of the R problems and T problems, and AP classroom problems, I've never seen an instance where you need more than that. The only thing you have to do is show that that equals that, and if they do, it's independent. Okay, so I already know that you're gonna ask me what's the difference between mutually exclusive and independent. You're not gonna ask me today. At some point, you're gonna ask me. Independence is a formula. I'm just gonna say, so you know, make sure you understand independence is a mathematical formula, which is this. Okay, and we're going to show independence, but we're going to use our variables switched. Does it matter that the variables switched spots? Guys? Well, think of it this way. The probability of the second thing given the first thing equals the probability of the first thing. This says the probability of the first thing given the second thing is the probability of the first thing. Meaning these two things need to match each other. As long as this letter matches this letter, you're good, is what I'm saying. So I said this A matches this A, I'm good. This B matches this B, I'm good. Doesn't matter what letter it is. All that matters is that those two letters match. Okay, now look back at your table that you made. What is the probability of B given A? Okay, A is male. So cover up the whole table except for the male column. What's the probability that you have a pierced ear given male? 19/90. And where did we get that from? Also on the previous page. So you guys understand where that came from? Okay, now what's the probability that they have a pierced ear? 103 over 178. I feel like we already calculated that somewhere. Oh, we did. It's 0.58. Are they equal? No. And it doesn't matter how far apart they are. It's just no. And since we got no from our table, that means we got the same answer. The answer is no. I want this one, but I did this different. Oh, I did. After the conditional.
Okay.
Okay, this last problem is just a preview for tomorrow's. But important still. We already covered everything we needed to cover for today, but this is a really good preview for tomorrow. Tomorrow's lesson is about tree diagram. So this is our first baby tree diagram problem. They're not that bad, I promise. But they're not, we don't make huge ones in really bad.
I'm pretty.
We didn't get one. We did them in middle school, and it was like, and there's branches, things about the branch, yeah, we're not. Oh, maybe it's not you. Yes, totally. You're like really master that. You like, you made that paper yours, when we're like. Okay, so once you guys get this in here, this is just a little baby thing. Then I want to add a little bit of notes to your yellow sheet. And you'll be able to use this yellow sheet along with your note card. Or you can just transfer these things to your note card. It doesn't matter. I just want you to have these things on your yellow sheet forever. Okay, you guys, we're almost done. Here we go. Consider this situation. About 55% of high school students participate in a sport. Roughly 6% of these athletes go on to play on an NCAA team. Okay, so what that means is it's 6% of these 55%. Let me say that again. It's looking for 6% of these 55%. Okay, and so what it's asking for is 0.55 times 0.06. So 6% of this 55% of meaning times is 0.033. So about 3.3% of the students play on NCAA. Okay, now how are we going to do that with tree diagrams? And this is what we're getting into tomorrow. The first thing you have is a sport and no sport option. It says about 55% of high school students participate in a sport. So I have 0.55. The most important thing you need to know about a tree diagram is all of the options need to add to 100%. So this has to be the complement of 0.45. It's forced to be, it has to be. Does that make sense so far? Okay, now this 6% is a conditional probability, means it's conditional on the fact that they play a sport. So 6% of those go on to play in the NCAA. I'm just gonna put nope on the bottom. I should put NCAA complement, but I'm not gonna do that. And 94% of those kids will not play NCAA. And so I want you to see how this tree diagram goes. You have a probability for your first branches, and then your second branches are conditional probabilities based off of your first branches. And you multiply down the branches, so that comes out to be the same thing. And we could find the rest of the tree. We can't actually find this. They didn't tell us anything about the kids that don't play a sport because that wouldn't make sense. They would not go on to NCAA probably if they did not play a sport. But anyway, this is kind of my opener for tomorrow's. All right, last thing. Once you get this situated, find your yellow sheet. And these are the notes I am allowing you to add to your yellow sheet. When we go to just using the yellow sheet on our test, you'll be happy to have these notes in it. Which if you forgot was the thing, let me remind you so that you don't have like stop. But does this make sense over here that I said if equals probability of A then independent? This doesn't fit make sense, like if that equals that, that's your independence formula. And they don't really have to be A and B, right? It's just the first two letters have, the first letter has to match. What's wrong? So like. Those people are equal. So I was just, I was people. Yeah, I wasn't sure how to. I got something. Okay, would you like me to see if there is a joke available?
Yeah. One more. Oh, well,
There's your joke.
It's like you guys did more.
It's his own diagram about himself. Probably not.
You would have loved it.
You would have loved it.
I should be on the quiz. Yeah, I think it's quiz, but.
No, because I like went to the back page, so when I came back, I was a little bit late.